Hi, I'm Meaghan Podlaski. I'm a graduate student working in the ALSET lab at Rensselaer Polytechnic Institute, and this is our work on multi-domain modeling for high-temperature superconducting components, or HTS, for the CHEETA hybrid propulsion power system. First, I'll go through the CHEETA electrical system architecture, and then I'll discuss the multi-domain model for the HTS components, the validation of those components, and the next steps with integrating those components into the power system. CHEETA is a program that explores future technologies in electrified aircraft. We're developing a hybrid electric aircraft that's powered by both batteries and hydrogen fuel cells. The aircraft's components are designed to be cryogenically cooled by liquid hydrogen. So we're developing an aircraft model that consists of multiple domains. We're considering an electrical domain, a thermal domain for liquid and gas hydrogen cooling, a mechanical and aerodynamic domain, and the controls of all of those components. Here, we'll mostly focus on the modeling of the HTS line in both the electrical and thermal domains. The HTS line is shown in orange and yellow in this aircraft model on the right. Here we have our electrical system architecture for CHEETA. It's a hybrid, centralized, and distributed electric architecture. There's 3 areas for propulsion. We have 2 sets of 8 motors on each of the wings and 4 in the body, providing propulsion. We have our fuel cells that carry power via HTS line to these drivetrains in both the wings and body. There's a battery connected at these distribution bus bars. This allows us to have more balanced weight of the aircraft by having the batteries located in the wings, and it allows for added reliability in case something were to happen to the HTS line and fuel cell. We have extra generation located right at that point. There's also a tie line between the fuel cells to add reliability. However, in this configuration, because we're using one HTS line to send power from the fuel cells to the bus bars, we need to cryogenically cool both the bus bars and the HTS lines so that we can limit the losses in those components. Here we have our cooling system. The HTS lines and bus bars are cooled separately from the drivetrains. This ensures a constant, stable temperature applied to the components. It also protects the system to ensure maximum capability to remove heat during a fault. In this flowchart here, we see that the motors, power electronics, and current leads take up most of the heat generation. So the power goes from, or the liquid hydrogen goes to the motor heat exchangers. In a separate loop, it goes to the cable conduit. They both heat up to the liquid hydrogen to a hydrogen gas, which is sent to the power converter heat exchanger and sent to another heater to control the cooling of the fuel cell at ambient temperature. Next, I'll explain the multi-domain models of the HTS components. We developed a transmission line component with a coaxial cable model in the electrical domain and a thermal model to dictate the surface temperature of the line. The resistances of the line are dependent on the surface temperature and cooling bath temperature, and the temperature of the line is held constant by a fixed boundary condition that specifies ideal temperature of the cooling system. So in the model below, we have our electrical model, which is encapsulated by our thermal system model with a thermal port to interface to the cooling media. First, when we model our HTS component, we model it with cold end cooling. We first need to determine the maximum current rating of the line, the resistivity, and the electric field. So the critical current is a function of the critical current at 20 Kelvin, and this value changes as a function of the temperature of the surface of the line and the critical temperature of the superconductor. The resistivity of the line is determined as a function of the electric field, the copper portion area of the line, and the critical current. And the electric field of the line is a function of a reference value, the current going through the line, and the critical current of the line multiplied by an index value for the line. Now that we have those values determined, we can calculate the pylon resistance, inductance, and capacitance. These values vary based on the line's temperature and carrying current. So the pylon resistance is a function of the electric field, the carrying current, the critical current, and an index value. And the inductance and the capacitance are a function of the geometry of the line, where B is the outer radius, A is the inner radius of the electrical cable, and Now that we have the electrical system models, we can model the thermal portion of the model. So we modeled the line for both liquid hydrogen and liquid nitrogen. The thermal system is nearly the same for both of these, with the only difference being the heat transfer coefficient. We model the heat transfer coefficient as a function of the nucleate boiling curve for both liquid hydrogen and liquid nitrogen. This heat transfer coefficient determines the heat generated by the line, where H is the heat transfer coefficient, and it's a function of the heat flow generated by the cable divided by the difference in temperature between the cable and cooling media. This nucleate boiling curve produces a piecewise function for both liquid hydrogen, and here for liquid nitrogen we get this piecewise function for the heat transfer coefficient. Now that we have the heat transfer coefficient for both medias modeled, we can model the rest of the cooling functions. These relate to interfacing the thermal junction to the cooling media. So we have the difference in temperature between the cable and cooling media shown as a function of resistivity, the critical current of the line, the geometry of the line where P is the perimeter and A is the area of the copper portion, and heat generation due to a potential additional fault and the heat transfer coefficient. The heat flow out of the line is a function of the heat transfer coefficient and temperature difference between line and media, and a cold end cooling function. This cold end cooling function is a function of the cooling bath temperature and the geometry of the line and the thermal conductivity of the cable. Now that we have the line model complete, we set up a circuit to validate the model's behavior based on previous experiments run on HTS tapes. So what we do is we apply a current source to one end of the cable and ground it on the other side. We ramp that current from 0 to twice the value of IC, and we test this for both liquid hydrogen and liquid nitrogen. Here we have the results where we apply the current from 0 to twice the value of IC. This helps us determine the where thermal failure would occur for each cooling media. Both lines have the same critical current of 3700 amps. Liquid hydrogen, which is shown in blue, cools the line until nearly twice the value of IC. This is shown that the temperature difference between the line and the cooling media slowly increases before sharply increasing at about 8500 amps. Whereas liquid nitrogen, this occurs when the line hits the critical current at 3700. This shows that liquid hydrogen does have some buffer included in the media itself, so we can size the line and include protection accordingly. And we can use the media as a form of protection as well. So, given an electrical architecture that's focused on cryogenic cooling, we defined a mathematical model for the HTS components that can be coupled with other multi-domain models to other portions of the aircraft. This allows us to integrate the thermal management and cooling system. Now that we have an early integrated system model, it's helpful at early stages to the development of the new propulsion concept. This allows us to identify the concept gaps and that liquid hydrogen is really helpful, and how to size the system accordingly early on in development. Next, we will model the bus bars. These bus bars are going to be made of a cryogenic metal to minimize the size and the weight of the system, and we'll integrate the bus bar and transmission lines to the rest of the system. We'll also need to couple this HTS transmission line to a dynamic fluid media model. Instead of assuming a constant boundary condition where the temperature is constant applied to the cooling media bath, we will include the model to have a dynamic fluid model. Okay. Thank you for your attention, and we'll take any questions in our session.